Hello and welcome to Module 2 of our Introductory R Programming course, where we cover the basic R data structures. This includes vectors, matrices, lists, and data frames. These are the fundamental R data objects that every R programmer needs to know inside and out. As usual, we have links to the code in the description, and I encourage you to download it, load it on your computer, and type in commands with me as we go along. Let's get started. To illustrate these concepts, we're going to be using a data set that includes information about the Billboard Hot 100 chart. These are the top songs of any given week, going back to 1978. The source of the data comes from this site, which I'll include a link to the description. And what you'll need to do, I'll also include a direct link that you can use to download the data. What you'll need to do is put that in your datasets directory on your computer. So the first thing I need to do is set my working directory. I've already done that down here. And then I'll look in the files and I'll see, let's see, I'm in the video code directory. Of course, to check that, you can always type get wd. And to get to data sets, I'll have to go up one and then down. Since I'm in video code, I'm here. I'll have to go up one and down into data sets to read in the data set that I want. And I've already gone ahead and subsetted the data to just 1 week in 1970, the week of April 18th. So to read that in, I'm going to call it Hot 100, read.csv, up into data sets, down to Billboard, and then I'm typing Bill tab, and that will complete it for me. Control Enter sends it over, and then I can start looking at the data. So the first thing I usually do is str. That prints out information, chart position, chart date. This is an integer, so this will tell us which position on the chart it is, if it's a number 1 or number 2 song. This is the date of the chart. It looks like this is always 1970, April 18th. The song name, the performer, how long it's been on the chart, so on and so forth. A bunch of interesting information. I can also take a peek at the data. And let's print out the top 10. All right, so here we go. So these are the top 10 from that week. Top song was Let It Be by the Beatles, and then Jackson 5 song ABC, so on and so forth. Wow, this was a pretty good week in music. Let It Be, ABC, Spirit in the Sky, John Lennon song We All Shine On, Badfinger, American Woman by the Guess Who, and Supremes. Wow, this is an interesting time in music. A lot of great musicians out there. Okay, so that's the data. That's at least the first 10 rows of the data. If we dim Hot 100, you can see this was already printed when we did str, but see there's 100 rows and 9 variables. And of course, if we do class Hot 100, this is a data frame. Okay, so data frame is one of the data structures we're going to be covering in more detail. You saw that last time as well, but we're going to start with a more basic type of object called atomic vectors. So let me make room here in the code. Okay, so one way, so there's various ways to create atomic vectors if you don't have one, or you can pull one out of an existing data set. And that's what we're going to do. So I'm going to create a variable called pos, and we're going to select the chart position from Hot 100. There's various ways to do that. We're just going to use $, and you can see the first one highlighted as chart position. So I'm going to hit enter to complete that. And if I want to print it out, I'll do that. So this is a vector. This is actually an atomic vector in R. You'll recognize that because of the way it gets printed out. it'll print out a number. So what this number means here, this is indicating that the first element, this is element 1 of the vector is consists of various elements. The first element is printed here. It's a 1. Just doesn't always have to be a 1, but in this case it is a 1 because the numbers run from 1 to 100. And the way it prints it out, it lists them out from left to right, and then it starts a new row. And to help you keep track of which element you're looking at, it will print the element number that corresponds to the first one here. So the 18th element of a vector from 1 to 100 is 18, so on and so forth. So this is how atomic vectors typically get printed out. This is a vector of integers, so they're numbers. We can also have vectors that are character strings, so hot $100 performer. Oh, we don't want to call that pos, we'll call that perf. These are the 100 performers. So what's happening here, how it's printed out a little bit different. The longest performer name, which I guess is Charles Wright and the Watts 103rd Street Rhythm Band, is more than half the width here. So what it does is it just prints each one on its own line, even though you could have fit Jackson 5 next to the Beatles here. So this is just the same thing. These are character strings instead of integers, and it's indicating which element you're looking at on the particular line. All right, why am I calling this an atomic vector? I think the reason for this name is because each element of this vector pos is indivisible. So if we look at pos, the 8th element, we can't break this down into a smaller thing, which is kind of what is meant by an atom. Of course, that's not true for atoms, but they thought atoms were atomic when they discovered them. Atomic vectors have the additional property that each element of the vector, so the 8th element of the vector is 8. So that's what I mean by element. Each element of an atomic vector has the same type. So with atomic vectors, you can't mix integers with character strings, with doubles, so on and so forth. So that's an additional property of the atomic vector. Now to get the type of the atomic vector, you'll type type of pos. Here it's an integer, and type of perf is character. Now let's look at the different atomic types. We're going to look at 4 different types. 3 of these we've seen before, but logical is a new one. It's very important. So let's create a logical vector. This is going to seem a bit strange at first, but I'll explain what this means. Hot 100 $ chart position. That's the same as pos. Less than or equal to 10. Okay, so what's going on in this line? This is an assignment. There's an assignment operator here. So what's happening is we're taking this thing and we're assigning the output of that to the variable top 10. So what's happening here is we're taking the vector chart position, this is numbers 1 through 100, and we're comparing that to the number 10, and the comparison we're doing is less than or equal to. So what will happen here is we'll look at each element of chart position, we'll compare it to 10, and what it's going to return is whether or not that particular element is less than or equal to 10. So that's a long explanation. If you see what it does, it's kind of obvious. So top 10, let's first print out chart position. You know what, I should use my variable names. So we already defined this to be pos. And pos is that thing. And if we run this line, now we have a new variable called top 10. And what it's doing here is it's looking at this element. Is this less than or equal to 10? Yes, it returns true. looks at this element. This element, is it less than or equal to 10? Yes, returns true. So on and so forth. When it gets to 11, it looks at that number. Is it less than or equal to 10? No. And the 11th one, it returns false here. And of course, the rest of them will be false. So this is a logical vector. It could take two values, true or false. And let's type here to print it out. We already did that. And if we do type of top 10, type of top 10 is logical. All right, so that's our first kind of most basic atomic type is logical. Integer, you've seen before. So let's just say type of pos is an integer vector. Doubles can include decimals. So if we do, let's just call it E is, and we'll create one because we actually don't have any doubles in this particular data set. 4.3, 6, 9.2. Run that. That's E. Gets printed out the same way as the others. And type of E is going to say double. So integers are numbers, minus infinity to infinity, including 0, 1, 2, 3, 4, 5. Doubles are decimals. They're also called floating point numbers. That can include decimals. And the last one we'll look at is characters. We've seen this before. Let's see, type of, so perf, this is the performer. Type of perf is character. Now there are some special values for each of these types. So let's take a look at these. Special values we're going to look at are NA, which is used to indicate missing values. Null, which is kind of a length 0 object. We'll show you what that means in a second. It serves several purposes. NaN stands for not a number. This is like representing a bad value. And we have the infinite, so minus infinity and infinity. So let's make some of these. So has nulls. Oh, there's some NAs in the data set. Let's look at those. Hot 100. Chart debut. Or in a previous week, I believe, has some NA. So let's look at this. So what are we doing in this line? We're taking our data frame. We're using square brackets to subset it. We're grabbing every row, comma, and telling it which columns we want to take out. So Control Enter will run that. It prints it over here. So here's our subsetted data frame. And the first column is previous week. That means what was its position on the chart in the previous week. And this column says when it first appeared on the chart. So if you look down here, these all have values, but when you get closer to the bottom, you'll see some that say NA. And so what's going on here is this particular chart is from April 18th, and this is the date that the song first appeared. And so in the previous week, that means it was not on the chart, and to signify that, they've included NA to signify that it was not on the chart. So it's kind of like a missing value. And you can see most of these that are NA also say April 18th. This one doesn't. Apparently this song was on the chart before, then left it, and the previous week it was not on the chart. Okay, so the NA is to signify missing values. You might argue that in this case the values aren't missing. There's information in the missing value, meaning that it just wasn't on the chart. But that's another argument for another day. NA is to indicate missing value. All right, let's look at nulls. So I'm going to make a vector has nulls. 3.7 null 7.2. All right, so what's going to happen here is it's going to basically skip the null value. So if I do has nulls, print it out, it just skipped it. So we can think of this as a length 0 object. Let's put in some bad numbers. Has nans. Instead of null, I'm going to try to compute the square root of -1. I'm also going to try to divide 0 by 0. I'm going to do all the things your math teacher told you not to do. Log of -3. So this one is technically it's going to be an imaginary number. R does have support for imaginary numbers or complex numbers. We're not going to cover those. This is undefined object trying to define 0 by 0. You have to be more clear about what you mean. And of course, you can't take logarithms of negative numbers. So let's run this. And we get warnings here. Square root of -1, nans produced, log -3, nans produced. Well, let's see. Oops. You can see all three of those got evaluated to nan. So it told us it was going to change these to nans, the second one and the fourth one. And it didn't tell us about this, but it did it anyway. So not a number is different from NA. It's not to indicate that it's missing. It's meant to indicate some kind of bad value. You did some illegal operation, and it's telling you that the result is not a number. Okay, let's do infinites. So has infs. I'm going to do this. So instead of dividing 0 by 0, I'm going to divide 7 by 0. And I'm going to do a negative value too. 3.4 divided by 0. So let's print it out. Oh, and what did I do here? You can see I forgot to finish it. So run that, and here's our infinite values. So important thing to note here is that there are infinite values. R can handle that. And there's a positive 1 and a negative 1. So if you divide 7 by 0, R interprets that as positive infinity. If you divide -3.4 by 0, you get plus infinity. And infinites have interesting properties. If you say inf plus 3, you can't get bigger. Inf -3 is still inf. Inf, let's see, inf times 8, you get inf. Inf times 0, doesn't know what to do with that. So everything multiplied by infinity is infinity except for 0. And everything multiplied by 0 is 0 except when you multiply it by infinity. So that's a nan. R has special functions for checking for these various things. So they mostly start with is dot. So there's is, well, these pop up. So there's functions for checking all kinds of things. What we're going to look at is dot na. And remember, this is a lowercase na, even though the actual value is uppercase. Is.na hot $100 previous week. So this is going to return trues and false, which remember is called a logical vector. It's going to look at each element of previous week, and if it's an NA, it's going to return true. If it's not, it's going to return false. So let's take a look. So as you remember by looking at it, do we still have it here? Yeah, most of the ones at the top, in fact, all the ones at the top are not NA. And then you start to see NAs lower on the chart. That's because these songs are just entering the chart at a low ranking. And that's indicated here. So all these are false, meaning they're not NA. And then you start to see some trues show up at the end of the list. So that's for checking for NAs. Let's do is.nan, and we're just going to plug in our object has nans. So remember the last three were nans, and you get trues there. And you can check for finite. Is.finite has infs. Only the first one shows up as true, the 3.7. When it popped up, you probably also saw is.infinite. This should be the opposite. Okay. Now the next topic is very important. It's a source of bugs in your R code, so you really need to understand this. R does something like that's called automatic coercion, and let's put this down here so you can read it. So if you try to combine different types in the same vector, remember I told you before that you can't do that in atomic vectors, but if you try to do it, R is not usually going to give you a warning or an error. It will just automatically convert the values to be the same type. And the rules for doing it is it automatically converts it to the higher type. And this is the ordering for the types that we have seen so far. Logical, then integer, then double, then character. So what this means is if I try to combine a logical with a double, it's going to convert everything to double. And so let's see how that works. So let's just make a single value A be true and print it out. Okay, so that's A. And just to convince you, type of A, this is logical. And let's make a new value B, which I'm going to combine A with an integer vector. So 1, 2, 3. So what's going on in this line is we're combining this length 1 vector A, which is true, with a length 3 vector 1, 2, 3. So we can run that. That worked fine. There's no errors, no warnings, even though I'm combining a logical with an integer. And when I print it out, you'll see what happens. So the first element was true, that was A. When it combined a logical with an integer, it converted the true to be 1. Now let's see what happens. Let's do these two together. Let's redo this and say false, true. So now A is a length 2 vector, still logical. If we combine it with 1 to 3 and print it out, it converted the falses to 0 and the trues to 1. So 0, 1, then 1 through 3. All right, so let's keep going. D is we're going to combine B, that thing we just created, with a single double value, print it out, and do type of. So when we printed it out, it's indicating that these are double by including decimals. And if I do type of, it prints double. So it converted these integer values to their corresponding double value. And it kept the last one as a double. So the reason it's doing that is because double is a higher type than integer. So the rules is it always goes to the higher type. So let's do one more, and we'll combine that vector with a character, print it out, and do type of. All right, see what it did here is it basically just quoted everything, and it actually rounded before quoting. Well, it didn't round, it stripped the 0.0 before quoting because it kept 1.3 as 1.3, and then it just added ABC on the end. So character is a quote-unquote higher type than double, so when you combine a double and a character, you get a character. The reason for this ordering is that the conversion to higher always makes sense. So there's a rule that false becomes 0, true becomes 1. So if you combine logical with integer, that's fine. However, you can't go this direction. So actually R does have rules for going this direction, but it's not a simple mapping. So there's more integers than there are logicals, so it's hard to define a mapping from integer to logical, so on and so forth. All right, so that's how automatic coercion works. There's this hierarchical ordering of the different types, and you need to know about this because it could be a source of silent bugs. So maybe you accidentally combine a character string with your double vector, you don't know it, and then your code gives an error somewhere down the line because you didn't know it, and you have to go back and figure out why it's doing that. And the reason I say it's silent because it doesn't print an error when you combine types. Okay, so the reason R does this is that it can make your code simpler. So if you really want to do the coercion, it just does it automatically. That's fine. It also can make some operations easier. So let's do this. So if we want to do sum true, false, false. Of course, you can't add up what is true plus false. I don't know. So what R is going to do here is it's going to coerce to integer. So it's going to make this a 1, this a 0, and this a 0, and this should evaluate to 1. And you could do things like mean. This can be really useful for counting things in your data. So remember we had is.na hot $100 previous week. Suppose we wanted to count up the number of songs that were not on this chart last week. So what we would do is sum is.na hot $100 previous week. This is a very quick way to write R code to compute a statistic about this previous week. If you want to be explicit about your coercion, R allows you to do that. So they have functions for doing these manual coercions, and they all have sort of the same syntax. Let's do as.integer, lowercase c, true, false, false. This is going to do the coercion for us, 100. We also have as.character. All right, so I'm using some special things here. So 1.2312 pi is a special number that's special variable in R, gives pi. exp1 is the number e. Let's run this. exp1 is 2.72 roughly. So if this is going to be a double, but if we run as.character on it, it's going to convert it to character strings. So that's a convenient way to print out e to this many digits. There's also as.double. This isn't going to look very interesting, but that just looks exactly the same. Okay, so that's for doing manual coercion. You actually can go, so these are all going in the order of the hierarchy. So as.integer is converting logicals to a higher type. As.character is converting doubles to a higher type. This is converting integers to a higher type. You can do, let's see, there's a as.logical, 0 to 4. Let's see what happens there. All right, so the rule it uses is if it's 0, it makes it false. If it's bigger than 0, it makes it true. So you can manually coerce from a higher type to a lower type, but you have to double check on what the rules are going to be because it's not always obvious. In this case, that's what it does. All right, we're still talking about atomic vectors, and atomic vectors, like most objects in R, will have certain properties. So I'm going to show you some of the functions for getting and setting those properties. So let's make a vector called song10, just to have something to work with. Hot $100 song. These are the top 10 songs that week. There they are. All right, the first property we're going to look at is length. So you can guess what this is going to be. So length tells you how many elements are in the vector, and that should be 10, as we expect. Another property is names. This one can be really useful sometimes. So if we say names of song 10, it's going to give us null. Okay, so here's the first real life application of the null value. Basically, song 10 has no names. So the way R tells you that it has no names is it returns null if you call the names function on song 10. Now, names is a special function that this syntax is going to look weird to you at first. So let me just type it out and then I'll explain. Okay, that's the syntax. So the reason this looks weird is because on the left-hand side, I'm not assigning this to an object. So normally, like for example, up here, the left-hand side is a name of an object, and the right-hand side is a value. Left-hand side here is the output of a function call. So that's a bit strange. And of course, the right-hand side is still a value, the first 10 performers. So what's going to go on here is R knows how to recognize this. And what it's going to do is it's going to assign the first 10 performer names to the names attribute of song 10. So let's run that. So this is perfectly legal R code. And now if I type names song 10, this will return the names. It's going to be no longer null. It's giving the performer for each of those 10 songs. Now when I type out song 10, up here when we typed out song 10, it just listed the element number or the index number. Now instead of that, it's going to list the names. And it can't fit them all, so it just goes one on each line. So what we're looking at here is this is information about the first element of song 10. Song 10 is a character vector. This is the value in the first element, let it be. And this is the name of the first element, the Beatles. So this can be sometimes hard to look at because it just looks like a string of text. But the way you can decipher this is that the values are going to be quoted and the names will not be quoted. We'll look at kind of a simpler example to see what that looks like. All right, so that's the names attribute. Up here, we specified them with the names function. We can also specify them when we create the vector. So here I'm going to create a vector. This is just a stupid little vector. So I'm using the C function, but between each comma, I'm saying some name equals a value. So it's name equals value, comma, name equals value, comma, name equals value. So if I run this and I type B, it's going to look like this. So this is still a vector. I could do type of B. This is a double vector. So the type refers to the values, 3.590. But this is now a named vector. And we could do, we can also look at names B, for example. So this will return the names. And names are always going to be characters. And what's returned by names B is also a vector, but it's a character vector. So for example, you could type of names B, and this is going to return character. Okay. Now, you might say, okay, this is annoying. I don't want to print those names out. So you can remove them if you do unname B. Now, this is important. This didn't remove them from B. What this does is it returns a vector with the names removed from B. This is very important. So this, actually nothing happens to B on this line. This just returns a new vector with the names removed. So if I run that, it actually doesn't change B. If I want to change B, I actually have to type B equals unname B. And now B will not have the names. You can also use as.vector to remove the names. Well, actually, we already removed them, but if they were still there, that would remove them. We've already looked at subsetting vectors, but you can actually do this in ways that we haven't seen before, including using the names. So let's look at our song 10. So that's the whole vector. If we want to grab the first element, we'll do song 10 1. You've seen this before. If you want the first 3 elements, you could do 1 through 3. There it is. Those are the top 3 songs from that week. You can also use the name. So if I want to grab the song written by the Beatles, you could do song 10, the Beatles. And what it's going to do is it's going to look at song 10. It's going to look at all the names for song 10, and it's going to return the element whose name is the Beatles. So this should return let it be, and it does. So this is the value, let it be. This is the name of the value. And so, for example, if you wanted to get all the songs that included members or former members of the Beatles, you could do this. So that gets the Beatles and John Lennon's song, Instant Karma. If you want all the songs written by Paul McCartney, you would get Let It Be, whose name is the Beatles, and Badfinger. This song, Come and Get It, was actually written by Paul McCartney. The band didn't like it, so he gave it to Badfinger. If you want it, here it is, come and get it. All right, that's all the singing you're going to get. Let's see. You can also... Oh, this won't work. So here I'm trying to select the element called Let It Be from song 10. If I run this, I get NA. So what that's telling me is that there's no element named Let It Be. There is an element whose value is Let It Be, but there's no element named Let It Be. If you want to get that one, you have to type in the Beatles. Okay. So you can use character strings, but you have to use the name of the element, not the value of the element. You can also repeat values. So say you wanted to make a playlist and you wanted to, you liked the Guess Who a lot. So you wanted to make a playlist with Guess Who, and you wanted to play it twice, once at the beginning and once at the end. You can actually repeat numbers here. So what's going to happen here is this is going to return a vector whose first element is vector 9 of song 10, whose second element is element 2 of song 10, third element is the first one, fourth element is the fourth one, and the fifth element is the ninth one. So let's run that. Oops, that just ran 9. All right, so the first element is the ninth element of song 10. Let's print out both of these so we can see exactly what's happening. So there's song 10, and there is song 10 92149. So This is the 9th element of song 10. This is the second, ABC by Jackson 5. This is the first element of song 10. This is the 4th element, John Lennon song. And this is the 9th element repeated. So what we're trying to illustrate here is you can subset with integers. These are also called indices. This is the 9th index. And you can repeat them. So this can be useful sometimes. Now you can also use logical vectors. And to keep things simple, I should probably use logical vectors that are the same length as song 10. So let's just type this out and then I'll show you what happens. All right, now I got to count them up. 1, 2, 3, 4, 5. All right, that's 9. Okay, so this vector is a logical vector. Let's run this. Its length is 10, so I'll just count it up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, which is the same length as song 10. And the first element is true. The 4th and the 5th element are true, and the 10th element are true. Otherwise, everything's false. So what gets returned when you put this logical vector inside of square brackets next to song 10, it's going to return the 1st, the 4th, the 5th, and the 10th element of song 10. Okay, there we go. 1st, 4th, 5th, and 10th. This is also really useful for selecting data. So for example, say you wanted to get all of the short song titles. So there's a function called nchar for counting the number of characters in each character vector. So what is this returning? So this is saying let it be has 9 characters. Let's just verify. 1, 2, 3, space is 4, 5, 6, 7, 8, 9. So this character string let it be has 9 characters. That's why nchar returns 9. So say I wanted to get all of the songs with short names, let's say less than or equal to 15. This is going to look at this object, nchar song 10, compare each one of these numbers over here to 15. We're going to return true if it's less than or equal to 15 and false otherwise. Important, this is not an assignment. This is the less than or equal to operator. That would be assignment. This is less than or equal to. Very similar, but very different. All right, so let it be is less than 15, ABC is, and come and get it is also less than 15. So this is now a logical vector, and so we can put this inside of song 10 with square brackets. And this will select those songs whose song title has less than or equal to 15 characters, which is let it be ABC, come and get it. So this is something you're going to be using all the time when you're processing data in R. So really take note of this. And, like I said in the previous video, come up with something else you want to select by and see if you can figure out how to do it. That'll help you learn more quickly. All right, so that's a lot to say about vectors, but I think it's worth it. Vectors are the most basic of data structures in R. So if you understand vectors, you can get pretty far. And you'll also help you understand other objects as well. All right, so matrices are kind of like a two-dimensional vector. It's a 2D array of numbers instead of a single list of, list of numbers. There's a function called matrix for creating matrices. I encourage you to take a look at the documentation. So let's just use it. Let's create a matrix called M. I'm going to call the matrix function. And you need to give it 3 arguments. The first argument is what values you're going to put in the matrix. So I'm just going to put the values 1 through 8. The second argument is the number of rows. So I'll make it 4 rows. And the third argument is the number of columns. So what this is going to do, it's going to populate a matrix with 4 rows and 2 columns with the numbers 1 through 8. And it does it in a very specific way. It fills in the first column first and then the second column second. That's opposed to doing 1, 2, 3, 4. By default, R uses what's called column major ordering for matrices. You can't override that. So if I say matrix 1, 8, 4, 2 by row equals true, it will do it the other way. One, 2, 3, 4, 5, 6, 7, 8. Okay, matrices have a property called dim. This is kind of the defining property of a matrix, or its dimension. It will return a length 2 vector. The first element will be the number of rows, and the second is the number of columns. You can, just like you can name a vector, you can name the elements of a matrix. But instead of naming each individual element for a matrix, you'll name the rows and name the columns. So there's a function called call names. It works just like names in the sense that you can put it to the left of an assignment operator. And let's just be very uncreative and call it column 1, column 2. So if I run that and print out M, now instead of this square bracket, comma 1, square bracket, comma 2, it's now printed the column names. And we could do the same thing for row names. Now, instead of 1 comma, it's printed out R1, R2, R3, R4. Okay, so that's call names and row names. If we type class on a matrix, its class is matrix array. Array is kind of a higher level class that includes not just 2-dimensional objects, matrices, but 3-dimensional arrays as well. Okay, one of the concepts we've talked about already is the concept of recycling. This is a kind of an R quirk that you really need to understand. And we're going to show how it works when filling in matrices. So you can do things like the following. Matrix 1, 3. You're probably wondering this when I was typing this out. Okay, so what's going on here? I'm creating a matrix with 3 rows and 4 columns, so 12 total elements. But I'm not giving it 12 things to put in there. I'm only giving it 3 things to put in there. So what it's going to do is just going to recycle this vector 1, 2, 3 4 times to fill in the matrix. So let's run that. And here's what it does. So it goes 1, 2, 3, starts over, it recycles. 1, 2, 3, 1, 2, 3, 1, 2, 3. So that's how recycling can be used to fill in a matrix. If we did it this way, it's still going to go in column order, but when it gets to the end, it's going to start over at 1 here. Okay, so this can be useful for defining matrices with a small amount of code. Otherwise, if you wanted to do this kind of thing, you'd have to first put in a matrix, empty matrix, and then fill in the first row, the second, the third. This can be a faster way to do things. But again, it's silent. It doesn't always tell you that it's doing the recycling. If we try to do this, this will display a warning. So the reason it displays a warning is because the length of the input data, 1 through 5, is not a multiple, submultiple, or multiple of the number of rows. So the total number of elements is 12, and 5 doesn't go into 12 evenly. So it says probably you've made some kind of mistake in your code. So I'm not going to give an error. I'm going to give a warning. And I'm going to tell you what's going on. But it's still going to create it, but you'll get a warning. It does not give a warning in these two cases because R assumes that this is, if you make the input vector, if the size of the matrix is a multiple of the size of the input vector, that's something probably someone did want to do, and they don't give you a warning, even if you didn't want to do it. It can't read your mind. The way this is most commonly used, recycling, is to fill in an empty matrix. So if I want to make a matrix that just had full of missing values, I would do this. And that will recycle the value NA 12 times. Of course, any number of entries is going to be a multiple of a single input value. So this will always work and never give a warning. Subsetting is very similar to how subsetting works for vectors, except the difference is because a matrix is a two-dimensional object, we can subset matrices with two numbers instead of one. So here's our matrix, 1 through 8, a 4x2 matrix. If we wanted to pull out the this entry, what we need to specify is M first row, comma, second column. So this should give us 5, and it does. We can do multiple rows. So M, if we want the first 2 rows, we'll do M1, 2. If I leave the column blank, it will grab all columns. So this grabs both columns, but only the first 2 rows. If we do this, this is kind of interesting. 1, 2, say we just wanted the second column. All right, now things are printed out a bit different. So let's see what's going on here. If we do a class of this, this is a matrix. If we do class of this thing, this prints out integer, which is signaling to us that this is a atomic vector. Okay, now this can be another source of silent bugs. So suppose you have a function that takes in a matrix class object as an input, but you have subsetted some original matrix and converted it to, it automatically converts it to a vector. That may cause bugs in your code. There is a way to avoid this. This is maybe getting a bit advanced for us right now. If we do class, so this is the thing that returns a vector. If we add comma drop equals false, it will keep it as a matrix. So this printout is quite different from this printout, even though it contains the same 2 values. If we do class of this, it says that it's a matrix. Okay, so that's kind of getting into the weeds a bit, but that can be another source of silent bugs, that if you just grab one row or one column of a matrix, then it will automatically coerce to a vector. You can also do subsetting using row and column names, so let's just look at that. R1, so if you want to grab the first row, you can just put in the row name. If you want to grab rows 3 and 4, but both columns, probably you would just leave it blank, but this is just to show you can type in column names. that's that. So that remains a matrix. What you can't do is combine. So here's kind of a mix. I'm using indices, index 3 and index 4 for the rows, and I'm using names for the columns. What you can't do is combine names with indices. So suppose I wanted to grab the first 3 rows, and so the way I would do it was use the names for the first 2, and then 3 to grab the third row and all columns. This gives an error subscript out of bounds. So given what we've learned, see if you can figure out why this gives an error. And the hint is to kind of go through the order of operations. So what happens first is it evaluates this, and then it plugs this in as the rows to select. So I'll pause the video and think about why that happens. Okay, hopefully you'll see that when you do this, because of automatic coercion, move this up a bit. Because of automatic coercion, this is going to get changed to the character strings R1, R2, character string 3. And of course, there's no row named character string 3. And so this thing is going to be out of bounds. So this is a good example of automatic coercion at work. And it might look like it's doing something that's unexpected, but this is perfectly expected because it converted that 3 to character string 3. Up next, we're going to talk about lists. Lists are a lot more flexible than vectors because, well, we think of lists as non-atomic vectors. Remember, atomic vectors, each element of the vector is indivisible, and each element of the vector has the same type as every other element. When you're working with lists, both of those things go out the window. So you can have lists that contain vectors, and you can have lists where one element is a vector, another element's a matrix or something else. So let's take a look at lists in R. First example we're going to see is there's a function called dim names. And we're going to go back to our hot 100 data set. If we do, let's do head hot 100. All right, just to remind you what the data looks like. This is a data frame. It has column names, chart position, chart date, song, so on and so forth. It also has row names. The row names are just the number, 1, 2, 3, 4, 5, 6, up to 100. The function dim names gives you both the row names and the column names of a data frame, also of a matrix. So if you think about how it's going to store the row names and the column names, that gets a little bit tricky, because if we just store the row names as character strings and then put the column names after, it won't be clear that you could do that in an atomic vector, but it won't be clear where the row names end and where the column names start. So the way R stores the dim names is in a list. So let's run that. And so this is what a typical list will look like in R. This list has 2 elements. Element 1 contains the row names, which itself is a vector. Element 2 contains the column names, which itself is a different vector of a different length. Okay, so this is a list element. If you want to subset it, let's just call this dim n, dim names hot 100. If we want to select the row names, we'll do dim, and then we'll use double brackets indicated here, 1. This will give us the row names. And dim n 2 gives us the second element, which contains the column names. All right, so that's an example of a list and how you can subset a list. Oh, I put it below the comment. Let's just move this up. All right, so to create a vector, we use the function C. To create a list, the function is called list. So let's make up our own list here. In this list, the first element is going to be the vector 1 through 4. The second element will grab some of the performers, first 3 performers. And the third element, we're going to put in our matrix. So this is a good example of a list. The first element is a length 4 integer vector 1 through 4. The second element is a length 3 character string vector. And the third element is a matrix. So this is 3 kind of wildly different types of R objects, and we can put them all together in one list. So if we do A, print it out, we get this. First element 1 through 4. Second element, first 3 performers. Third element is our matrix we created earlier. Type A, and when we do class A, this should return list. We can also name our list. So if we take this piece of code, we can name this. So let's give this some names, numbers, perfs, performers, mat equals m. So this looks just like how we use C to name an atomic vector. The syntax is list, name equals value, comma, name equals value, comma, name equals value. If we run this, now instead of this double bracket 1, it's now printing out $name. And that gives us a hint about how to select elements. We could say a $mat to grab the mat element of that particular list. All right, so let's look more in detail about how subsetting works with lists. If you can use single square brackets with lists. So for example, if I do A1, this works. But what you can kind of guess by what we're looking at here is it's not actually returning the vector 1 through 4. It's returning a list whose first element is the vector 1 through 4. So we do class A1. This is still a list. And of course, this is different from, oh, we'll look at that in a second, but this is going to be different from this thing. See here, when you use double square brackets, it doesn't actually print out the $numbers, and that's telling us that this is no longer a list. This is the element in the this is the object in the first list element. So this is an integer vector. Okay. We saw before we can use $. Let's see. Actually, we can use $sign to select an element using its name. We can also use square brackets. So if I say perfs, this will give us the performers. Because we're using single square bracket, this is going to return a list. You can see that here. It's because it says $perfs. But it's a list with an element equal to the perfs element of A. We can also grab multiple. So if we want the first 2 elements, this will again return a list of the first 2 elements of the list A. Numbers and perfs, so it's leaving off the mat element. When we use double square brackets, we're getting the object in that particular element. So A, we saw this above, gives the first element of A, which is the numbers 1 through 4. And we can also do use the names. That should give the same thing. And we saw this above, but $sign does the same thing. All right, so when you use $sign, it selects the object that's in the element named, in this example, perfs. The last data structure we're going to talk about is the data frame. Now, of course, we've already talked about data frames quite a bit, but now that we understand what an atomic vector is, what a matrix is, and what a list is, we can better understand what a data frame actually is. So a data frame, you can think of this as a special type of list where each element of the list is itself a vector, and all of those vector elements have the same length. So for example, for Hot 100 is a data frame, the first element of that data frame, the first column, is chart position. This is a length 100 vector. The second one is chart date. That's also a length 100 vector. And this one happens to be a character vector. So what a data frame does is it's sort of like a matrix, except that the different columns of a data frame can have different types. Whereas in a matrix, all of the elements of a matrix have to have the same type. You can see it's kind of like a list because we're subsetting using $. We'll see down below that we can also use the other list attributes to subset. And we'll also see that you can subset it like you would subset a matrix. Okay, so what happens when we do names of Hot 100? So I'm going to tell you before we run this that this function is treating Hot 100 as a list. Just to remind you, row names Hot 100 is this. Call names Hot 100 is that. So the question is, what gets returned when you call names? Because I'm not specifying, is this row names or is this call names? What returns when you just say names? If I give you the hint that the names attribute treats the data frame as a list, you could probably guess what this is going to return. And it returns the column names. And the reason you know that is because each list element is the vector, the column vector, giving the data for that particular column. Okay, if we do length, this will also treat data frame as a list. So if you're thinking, what is this going to return? Length of Hot 100. It could return how many total elements are in this data frame. But if I tell you ahead of time this attribute treats the data frame as a list, you should know that it's going to return 9, which is the number of columns. Okay. So what a data frame is doing, it's sort of like a list where each element of the list is a column. And therefore, when you do names, it gives the column names. When you do length, it gives the number of columns. Other attributes treat it like a matrix. So if you do n row Hot 100, it's going to know that you're looking for the number of rows, which is 100. N call Hot 100, it knows you're looking for the number of columns, which is 9. Similarly, subsetting, when you subset a data frame, you can treat it like a matrix or you can treat it like a list. Let's do the matrix first. So remember, matrix subsetting, you'll do square brackets and put a comma and say which elements you want. So if I want the element in position 1, 3, that returns let it be. Let me just remind you. All right, here's head Hot 100. Element 1, 3 would be row 1, column 3. So this is row 1, column 2, column 3. This is the value let it be. Okay, so this is working just like a matrix works. You give square brackets and you give two things separated by commas. You can also grab multiple rows, multiple columns. All right, so this gives chart position, song, performer by grabbing the first 4 rows and columns 1, 3, and 4. All right, so that works just like a matrix. Now you can also treat it like a list. So if I do hot 100, we've already seen this chart position, or chart date, why not? This is treating the data frame as a list with 9 elements, each of which is an atomic vector. So that's that one. Just like a list, you can use double square brackets to subset. So if I do chart position, this is returning the list element or the column whose name is chart position. Now, if I do single square brackets, I'm going to get something different. Now, before I run this, you should be doing this all the time. Try to guess what this is going to return. So when we used lists, when we used double square brackets, it returned the thing that's in that element. When we used single square brackets, it returned a list that contains things. So this returns the column chart position. What is this going to return? Well, it's going to return a list because it's using single square brackets, but because it's a data frame, it's going to return a data frame. So let me run this. And what it does is it returns a data frame whose one column chart position, and we can verify that by saying class hot 100 chart position data frame. Whereas if we do class hot 100 double square bracket chart position, this returns an integer vector. Now things get kind of tricky, so you can say hot 100, if you want to grab 2 columns, chart position, song. This is using single square brackets, but it's going to treat this like a matrix. So it's going to grab all rows, these 2 columns. So this also returns a data frame. You can see by the way it gets printed out. And it actually gives the same thing as this. So these are exactly the same call, except this one does all rows, comma. This one is treating it like a list. It's grabbing the list elements named chart position song, and because it's single square bracket, it's going to return the list version. It's going to return a data frame. Run that. So this is also a data frame. Okay. All right, so the thing to remember about a data frame is you can think of it as sort of like a matrix, but it's different in the sense that the different columns can have different types. It's sort of like a list, but it's a special kind of list where each list element is a column, and each of those is an atomic vector. Each element is the same length, and it has the same type within the column. All right, so let's use what we've learned today, and I want to show you how we created this data set. So let's pull up another file. Intro R, video code, subset hot 100. So the full data set is called hot100.csv. If I run this, see this takes longer to load in because it's very big. So dim dat, it has 336,000 rows and 13 columns. So the way I created this smaller data set from 1970, April 18th, is I subsetted this larger data set, which contains data from every week going back to the 1950s. All right, so the first thing I did is I used a comparison operator to find all of the rows for which the chart date was equal to the date I selected. And this is the first time we've seen the double equals sign. So double equals is different than single equals. Remember, single equals can be used for assignment, either to objects or to arguments within functions. When you use double equals, this is a comparison operator, meaning we're taking each element of chart date, comparing it to this value, this character string, returning true if they're equal and false if they're not equal. Before we saw something like this, that's less than or equal to. This means equal to. So this double equals a comparison operator. It's not an assignment operator. So if we run this, we get this big long thing, II. So this is length 336,000. We can operate on this. So for example, we could do sum II. Before I run it, think about what that's going to return. It returns 100 because there's 100 songs, basically the top 100 that occurred in that week. Next, we're going to specify which variables we want to keep. There's some other variables if we do, let's see, if we do head hot 100, just to make things, head dat is what we called it. There's some other things in here that we didn't need for this illustration, namely a song ID and a URL, but that's all there in Hot 100. So we're just grabbing these columns that I'm assigning to a variable called vars. So this is vars, those are the columns we're getting. And then we do the subset. Now I'm taking dat, which is my full data frame. I'm subsetting using a logical vector here and using column names here. So that's perfectly allowed. You can mix rows with one method of subsetting and columns with another method. What you can't do is mix different types of subsetting for rows and different types of setting for columns within the column subsetting like we saw before. I'm assigning that to dat2. And if I do head dat2, I didn't like how this looked because it didn't make the first one, the first row, the top rated. So I used the order function to take the chart position of dat2 and reorder them. So that's what this does. Let's actually look at this. So ord. So what this is telling us is that the 51st element of chart position is the #1 ranked song. So if I do, let's see, ord 51, sorry, not ord 51, dat2 51, this is the song Let It Be, which was the #1 ranked. So, and then the second one, dat2 2, just by accident, this happened to be in the second position. That's ABC. And dat2 77 is Spirit in the Sky, Norman Greenbaum, which was the 3rd ranked that week. So order is it kind of reorders things for you. And so if I do dat2 ord, what it's going to do is grab the 51st row of dat2 and put it first. Second one, put it second. 77th one, put it third. So this will reorder things how I want them. So now if I do head dat3, now it's in the right order. And now the only remaining task is to write it to CSV. So I'm going to define the file name. Of course, you can do this all in one line, but I thought it looked nicer to define it this way. And I call write CSV on dat3 to write it. Okay, so that's how I created it, and I used a lot of the lessons from this particular video to actually do that, to do actually something useful that I had to use in real life. So this stuff, you really need to know it. Okay, that's it for this module. We covered the basic R data structures. That includes atomic vectors, matrices, lists, and data frames, and they're all kind of related to one another. And kind of the key thing to put together at the end of this was that a data frame actually is a special type of list whose each element is a column, and each of those columns has to be an atomic vector, and they all have to be the same length. All right, so once you understand that, you're really well on your way to understand what's going on in R. All right, until next time.